Hello everyone, my name is Ul Haq and I'm a faculty at the Department of Physics at Syed Babar Ali School of Science and Engineering at Lahore University of Management Sciences. Today I would talk about quantum-inspired technologies, a vision which is not only driving my own research but also that of my fellow colleagues at the Physics Department, including Professor Sabi Anwar, Dr. Adam Zaman and Dr. Ammar Ahmad Khan. So the question is, why quantum technologies or quantum-inspired technologies? Global race is going on among advanced economies to achieve supremacy in quantum technologies. It is the 21st century version of the space race. The race towards quantum technologies is more evident in the efforts being put together to realize powerful quantum computers. Even big companies have jumped in. The promise is not limited to computing itself, but this technology is predicted to bring profound changes in communication, meteorology and sensing, and simulation technology. Groundbreaking nature of the research in quantum technology means that countries are willing to invest big in quantum research. Big economies of the world have pledged around 22 billion US dollar to be spent on the research in quantum technologies in the next 5 years. New research collaborations in the field among advanced economies are shaping up, resulting in an exponential rise in the publication in quantum research in the last few years. Our own region, India, for example, is investing big, and Iran is also among those countries which is trying to adopt these technologies. We think that investing in quantum research can really upgrade the current research profile of Pakistani research institutions and educational institutions. Uh, for example, utilizing the quantum resources like coherence, superposition, and entanglement, not only you can design innovative devices, but also you can do profound improvement in the material design as well. Not only the fundamental phenomena research would benefit from it, but the resultant instrumentation needed for this research may enhance the instrumentation profile of our research institution as well. Furthermore, this research can really benefit some of the key institutions in the countries. For example, SOPARCO, which is the country's sole-most commission for research in upper atmospheric research and also space research, can really benefit by investing in quantum satellite communication. Our strategic institution would be another beneficiary along with the quantum science education in the country, which can gain big from such research. You can also have industry which can benefit, although we do have a very nascent physics industry, but we can really develop our industry based on quantum research, and we can develop new standards. For example, the Standard and Quality Control Authority can benefit from the new metrology standards being developed by quantum research and bring it up to speed with the international standard, which would be hopefully in near future. Pakistan has a very thriving photovoltaic research community. They can benefit big from quantum research by overcoming the limitations they encounter in material and device designing via classical material science and engineering methods. Pakistan has a very large nanotechnology and nanomaterials research society as well, mainly because Pakistan invested a lot after 2000 into the field. However, the novelty of the field is receding, which means that even though the output of our research community is large, the impact of the work is overall decreasing. So therefore, the community need an impetus, and quantum research can provide that boost to the research profile, thereby increasing the overall impact of the work coming out of Pakistan. Then there are national institutions whose agenda directly fits into the quantum research itself. For example, the National Institute of Laser and Optics, which is doing research in quantum optics and optics, and the quantum research would directly benefit this institution as well. So why should the School of Science and Engineering as a whole should be interested in the quantum research or quantum technology? And the simplest answer to that would be that at least 4 of the physics faculty at LUMS have done research in quantum technologies or also currently doing research as well. For example, Professor Sabi Anwar, he has been doing research in quantum computing and practical implementation of quantum computing schemes via spin physics for almost the last 20 years. Myself, I've been involved quite heavily in the field of using nanostructures in the research of using nanostructure for quantum technological applications. Dr. Adam Zaman Chaudhry, he is a theoretician in our department, and he has done extensive theoretical work in the field of quantum control and quantum metrology. And Ammar Ahmad Khan, who has done work on optoelectronic devices involving or integrating quantum material inside these optoelectronic devices. So the physics faculty, at least 4 of them, have vested interest in the research field itself. Let's have a look at what are some of the current research themes these faculties are pursuing at the moment. In terms of device development and device physics, mainly experimental work, we are pursuing development of a prototype quantum light source, research on realization of stationary qubits, research on fabrication of quantum integrated circuits, in which these quantum light sources and qubits can be integrated. Then we have research on spin sensors, purely optical based spin sensors, and then optical sensors for quantum magnonics. Then there is research on quantum materials and research on magnetometry with nitrogen vacancy center and diamond. On the theory side, we are pursuing quantum parametric estimation, which is the theory of finding the ultimate limit you can achieve or the ultimate sensitivity you can achieve with detecting devices in terms of the quantum limits. Then we are pursuing quantum control schemes, which are the schemes used for control of qubits for quantum technological applications. So as a whole, if we look at a spread of these different topics we are working on, they comes into the realm of quantum computation, quantum communication, or metrology. For example, quantum light source is one of the main resources in quantum communication technologies. Similarly, a stationary qubit is a resource in quantum computation devices along with photonic integrated circuits. Apart from quantum materials, which is a research in basic material physics and the quantum mechanics of materials, the rest of the topic we are pursuing are more closely related to the technological application of quantum mechanics itself. Apart from these topics, we are also involved in educational endeavors. For example, the physics department has recently developed a teaching lab based on the exploration of quantum nature of light, exploring the Bell's inequality test and the quantum state measurement, for example. And along with that, we as a faculty have designed and taught courses in the last few years which are directly related to research in quantum technologies. We have, as an experimentalist, also tried to develop our own instrumentation which can be used for quantum research. For example, micron and submicron spectroscopy techniques and other scanning probe techniques which we have developed in-house for such kind of research. Perhaps the most only missing area in quantum research at the moment in the department and as a whole in the school is that of quantum algorithms. Apart from that, we have most of the bases covered. To give you an overview of the kind of work we are doing in our department, so we are doing material development, for example, higher crystal growth material using chemical vapor deposition and other techniques, which helps us in fabricating devices for quantum light generation, and which would also be instrumental in development of quantum photonic circuits. To explain those quantum devices, we are doing theoretical work which explains the nature of those quantum devices which we are currently working on. And apart from this, we also are doing simulations to design quantum materials which can be made or grown by these, for example, chemical vapor deposition technique. And once we have that, then we can study them or characterize them via ultra-fast optical spectroscopy techniques, which helps us identify the quantum character of these materials. So they are different than the usual material because their overall character is defined by quantum coherence and entanglement. This characterization helps us to understand the spin structure, for example, the magnonic behavior or the spintronic behavior of these quantum materials. So overall, as a result of this work, we are building a capacity within our department for quantum research. Along with that, we are working on teaching laboratories to study those quantum phenomena, and we also have did teacher training workshops to train teachers from schools and even universities to train them in quantum science and engineering. So as a whole, the agenda of our department is to not only increase our capacity building, but also get involved in training and teaching, which would not only benefit the overall scientific and academic community, but it may eventually help the scientific industry as well. Our vision of the faculty who is working in the quantum research is that we want LUMS, and then specifically School of Science and Engineering, to be a national and regional leader in quantum-inspired technologies in the future to come. So let me give you a brief overview of the current research we are doing LUMS. Let me start with the quantum light source. We want to develop a prototype quantum light source which is compatible with telecom technology and which can generate single photon sources. So we have already done some preliminary work on this and been successful in working using two-dimensional semiconductors, not only single photon signatures, for example, bound exciton in these two-dimensional materials, but we have also been able to develop arrays of these single photon emitters. Apart from that, we are also have start working on integrated photonic circuits. We have already made some preliminary circuits, but what we plan to do is to further develop waveguide and couplers and a whole network of photonic circuits integrated into one big chip, into which these single photon sources can later on be integrated. Apart from generating quantum light sources which emit single photons which can act as qubits for quantum technologies, we are also working on stationary qubits, more specifically solid state qubits. So the idea is to realize a solid state qubit which can be optically controlled. So what we are working again on two-dimensional semiconducting system in which which are truly atomically thin layers of semiconducting materials, and we use the value degrees of freedom which is coupled with the spin of electrons in these material, and using incident light or the polarization of incident light, we can initiate or initialize our system into one electronic value k or another electronic value k prime. So you really have a qubit system which can be initialized. The qubit fidelity, initialization fidelity we have reached at room temperature is around 20%. So these are the two main themes we are, me and Ammar Ahmad Khan, we are currently following. Dr. Azam Zaman is doing some important work on quantum parametric estimation to measure the limit of sensitivity we can achieve in terms of measurement with quantum devices, for example, NV centers in Diamond. We are currently also doing a collaboration in which we want to realize some of those measurement schemes. He has published extensively in the field in the last few years. Apart from that, he has also worked on quantum control theory, in which the coupling of a qubit with the environment and the effect of that coupling on the quantum computing operations are analyzed, along with different schemes, control schemes, which can be realized to minimize the effect of the system environment coupling, and then measure the dynamics of the system in terms of time to realize schemes for quantum information technologies. The important thing here is that he has published a lot of this work along with along with undergrad students. Professor Sabi Anwar is pursuing the field of optical spintronics and quantum mechanics, in which they have developed devices for optical detection of spin orbit coupling. They can also able to do single photon level Faraday rotation measurement to measure the state and the process of this rotation process. And they want to pursue the field of quantum mechanics in future as well, for which they have already worked on developing high resolution magnetic optical microscopy systems. Apart from that, there is a fundamental work going on in quantum materials. Materials which fundamentally depends on quantum mechanics to explain the overall behavior. These include the 2D or the two-dimensional materials which they are theoretically pursuing, along with some of the future goals which involves growth of topological insulator in two-dimensional material using chemical vapor deposition, a technique which they are recently working on. Apart from some of the characterization techniques like ultra-fast spectroscopy, they want to develop in future towards this goal of characterizing quantum materials. On the instrumentation side, we have tried to be as self-sufficient as possible and have tried to build an ecosystem of developing home-built setups like home-built scanning probe techniques like STM and AFM, and also in-house developed microphotoluminescence and micro-Raman setups for investigation at nanostructure of quantum devices. On the quantum education side, Sabi Anwar has been working on development of a quantum mechanics single photon lab, which has developed various experiments for demonstration of quantum nature of light, the fundamental test of quantum mechanics using photons, and a measurement of the states of photons itself, for which they have developed an array of those experiments and demonstrated practically as well, and a book has recently been published in that direction. Apart from the outreach work which they are doing for the last few years to teach the teachers in the country those quantum measurements and their implications. On the education side, we have also been consistently exposing our graduate students to cutting-edge quantum technologies and research in quantum science. We have developed courses like atomic and laser physics, quantum optics, quantum information, and quantum engineering, and we have been designed that specifically to emphasize the research and technology of quantum mechanics. As a result, some of our students have went on into the field of quantum information and communication and metrology in very well-known institutions. In summary, we are working on three different quantum systems. Those are spin, artificial atoms, and photons. We are not only working on initialization of these quantum systems, but also control and measurement. We do encounter some challenges. For example, the fidelity of our Wally spin qubit is currently limited to 20% because we can't go to lower temperatures to measure that. Or our quantum material development, because they do have dynamics which are extremely fast. We need ultra fast spectroscopy to see the physics inside. Or for single photon sources, we don't have the ability to go to lower temperature, so the single photon signal is relatively very weak. So the major challenges in terms of synthesis, characterization, and quantum measurements are that we do have developed the synthesis of techniques for high crystal quality to get the quantum materials, but we are currently lacking, for example, XRD for thin films to measure the quality of those films, or we lack the femtosecond laser to characterize the ultra fast processes in quantum materials, or we don't have a vibration isolated cryostat to study or to get quantum light from a single nanostructure. The quantum research as a whole is a very resource intensive research in itself and need a lot of funding. Some of the funding avenues we have sought are most prominently the National Research Program for Universities by Higher Education Commission has been our main resource for funding. We also submitted a grant proposal of Quantum Technology Lab to Higher Education Commission, which was not only approved, but also the physics department of LUMS was selected as a leading group in that national call for nanoscience and technology. However, due to some political reasons, the funds were not materialized. The potential funding opportunities we see in future is in this recent understanding between HEC and Max Planck Institute. So we foresee kind of an initiative like the Max Planck established tandem labs in South America. So we see a similar kind of opportunities, or hopefully to be pursued later on in future. Along with that, we are also trying to highlight the importance of quantum technological research to national strategic goals, and we are trying to do it by highlighting, by recording videos aimed at national strategic audience. So just to summarize, some of the physics faculty at LUMS have a very strong interest in quantum research and quantum technologies, and we are covering various aspects of quantum technological research apart from contributing into the education of these technologies and the instrumentation involved therein. The only missing point may be quantum algorithms or quantum theoretical quantum information, and hopefully that is an area which can be of great interest for an interdisciplinary hiring, which might increase the collaboration between the computer science and physics department within the School of Science and Engineering, and such a collaboration would fit nicely with the no boundary philosophy the school is pursuing. So with this, I would like to finish my talk, and hopefully I've been able to convince you that quantum technology and quantum research is something which School of Science and Engineering should really own, because as a school there's a lot of potential and a lot of promise, not only for the school but as a country itself. So I thank you for listening to my talk.